Does anybody have questions before we look? Yes.
6.2.
Which one?
Mindscape 15.
Someone is thinking of a connected graph in a plane. It is made up of 31 edges and cuts the plane into 17 pieces. The pieces are the faces. So there's 31 edges, 17 faces. How many vertices are there? You probably have different numbers though, don't you? So I'll use your numbers. And here's a reminder that you can go to the study group to meet today, 2 o'clock, or Monday at 2 o'clock. Quiz is on Wednesday, so Monday's a review day, and you should bring your review printed out to write on, unless you like to do it electronically. Okay, so you had...
my numbers are 34 edges and 13 pieces.
So we're using the Euler's characteristic of connected graphs, and we have V that we're looking for, 34 edges, and 13 pieces. So you can combine the two numbers. The one is negative though, so you'll have 13 minus 34 in your calculator, which is negative 21. So V minus 21 is 2. And then you would use algebra and add 21 to both sides of the equation. Or you can do it intuitively and just think, what do I subtract 21 from to get 2? Did you try that one?
No, I didn't.
Okay. Let me know later if it doesn't work. Any other questions? Yes?
On 6.2.
Which one? 2. Yours has different shapes? So you can show me yours after class if you want. On this one, you would count the little dots. So the dots are the vertices. 1, 2, 3, 4, 5, 6, 7. And then this dot is cutting this into 2 edges. So you have 1, 2, 3, 4, 5, 6, 7, 8 edges. And the faces on this one are 1, 2, 3. 3 faces. So I'll check if I counted wrong by clicking submit. And you can show me yours later if you'd like, if it doesn't make sense yet. Whoops. What did I do? That wasn't what I wanted to do. Maybe if I make it smaller, I can see better. Where do I hit submit? Anybody have any ideas? To the left?
Go to the right.
To the right. Should it be on the right bottom?
Yes, right on.
Oh, there it is. Okay, thank you. Okay. Any other questions? Yeah.
I just have a question about my Wiley Plus. It won't let me get on it. I'm not sure why.
If it won't let you log on, you should try another browser. Or wait, did you have an idea?
Yeah.
Okay.
Yeah, they're gonna try to show me how.
Okay. Any other questions? Okay. Also, you can call them. Let's see, if you go to the home page and you can't log on, there's still a help button right here or a contact us button. So even if you can't log on, you can I'm talking the online students. You can still call them, okay, for help. Any other questions? Well, we're going to look in section 5.2. What we're doing in chapter 5 is called topology. So I brought my topology book from when I was in my master's program. So sometimes when we do work in our class, it feels like there's not any numbers involved, especially when we're in the geometry section, and it'll probably feel like that today. And I did want to show you that there is in fact numbers involved. So if you look through my book where I learned how to do topology, there's lots of numbers, lots of formulas to work with, even though we're not seeing it because we're not doing those parts of the problems in class today. Also in the topology book, when I picked it up and looked at it, I saw something that reminded me of the life lessons that your author's working to show us. So here we have much progress in mathematics as a whole, not just in topology, has been the result of abstraction of ideas to their basic elements. Reduction to basic principles strips away superfluous and confusing information. It leads to simplifications and the unification of ideas once thought to be completely separate. And that's actually what we did in section 6.2, and that's why that jumped out at me. When we make these connected graphs that just look like squiggles with points, they're actually representative of connections between items or objects or places. And so the vertices are like the objects and the edges are like the connections, and that's stripping away the superfluous to look at the essential. So we're going to work today with a lot of hands-on work. So you need some paper and some tape, and I brought an extra set of tape and extra set of scissors. So I'll put one over here, one over here. So if you did not bring the scissors and tape, then go take your own piece of paper over there by the scissors, and be prepared to cut 4 strips of paper, because the first problem here, where we take a strip of paper and tape the short ends together to make a loop, we'll need 4 strips of paper cut. So if you don't have your own and you're going up to use mine, then you can cut 4. If you do have your own, you can cut 4 to start out also, because we will need 4. So you just, we'll look at a wide angle here. We're just using strips of paper about 1 inch, okay? And if you're coming up front to get one of mine, cut 4 about 1 inch.
I brought the tape and the scissors.
Oh, okay. So you have tape?
Yep.
Where did I put them? Are they behind you and someone took them already? Okay, then there's another set over there. Okay. Okay. So just start with 4 little strips. And we may make more later. I can't really remember exactly how many we use. And then take a bunch of little tape tabs on your fingers back to your seat after you cut out the little strips. So you got some tape tabs. I think the scissors maybe migrated. So put the scissors back where they were for everyone to use after you're done. So the life lesson today is to build physical models and perform experiments as a way to make new discoveries. So that's what we're going to do. Build physical models and use those for experimenting. So take one of your strips of paper. Let's see if I can get some background for it. That's a good idea. Yeah. But now your hands are full.
I'll be back.
Okay. So take one of your strips of paper and we'll make it into a loop. So you don't have to have all of these done at once, okay? So we're going to make a loop. Okay, so you take your paper and put the tip in the tape, and then make a loop by putting the other tip in, and we're getting plenty of tape here then. Now you've probably done these before, right? Has anybody else made counting chains? We used to make counting chains to count toward Christmas, right? You pull off one loop every day till Christmas, or maybe till your birthday. I'm thinking of doing it for retirement, but I thought that might just get depressing, so I haven't done that. Okay, so we make these loops, and I want you to examine the loop. So we have a physical model we can examine. Let's go ahead and write down what we see about it. So we're in 6.2. We'll call that a plane loop. The actual name for this is a cylinder. And we like to quantify things in this class. So we're going to look at the plane loop. We're going to look at the plane loop and count the edges and count the sides. Okay, so how many edges does your loop have?
One.
So one here and one here.
Oh, never mind.
Two edges. And how many sides does it have? Yep. 1, 2. Okay. So it has 2 edges and 2 sides. And now we notice what the actual question to start with is, how many pieces do you get if you cut the loop down the middle? So let's write down what happens when you cut the loop down the middle. What happens when we cut this down the middle? So some of you are borrowing scissors, you might have to come up and get some again. Okay, so when I mean cut down the middle, I don't mean crosswise, I mean lengthwise. So you maybe crimp it and then cut. So write your prediction down. What do you predict is going to happen? So write down what your prediction is. And then see if your prediction is right. Okay, is that what you predicted? Who predicted that? Anybody? You're like, yeah, I knew that. I saw that coming. Okay. So we have two loops, 2 cylinders. So when we cut down the middle, the result is 2 cylinders. Or 2 plane loops. Well, that was kind of boring. So now we're going to do something that is more interesting. So we're going to take and make a new loop, but it's going to be a little different. So this time, don't make a plain loop. This time, take your tape and put it on one side so you're ready to make your loop. So you're ready to make your loop, but you're going to put a half twist in. So I turn this side over. So I'm ready to connect these, but instead of just connecting them like I did before, I turn this side over. So there's a half twist now. Instead of just connecting straight together, I flipped this over. So one side and then I flipped it over. So let's go ahead and write down what we know about that. has a loop with a half twist. So now we have a loop with a half twist. Has anybody ever seen one of these before? Maybe if I tell you what it is. This is called a Mobius band. Have any of you seen a Mobius band before? Okay, well, let's take a look at what the Mobius band is like. Okay, so we have a Mobius band. Let's count first. Let's count the number of sides. So this is where you need your marker, because we need to keep track of sides here. So if you have a marker, that's exactly where we need it. So we're going to keep track of the sides. So I'm going to take my marker and run a line down the middle. And that will help me in a little while when I cut it anyway. So I'm going to draw a marker down the middle to count sides. So I can see it's on the other side of my paper, but I haven't gotten back to it yet. So I'm still on the first side because I have not returned to my marker. I just can see it bleeding through the other side. Now I returned. Now I return to where I started. So how many sides does the Mobius band have? Yeah, the Mobius band has one side. So that's a different thing right away. A plain cylinder has two sides, but a Mobius band has one side. In fact, because a Mobius band has one side, sometimes it's used as a conveyor belt. So if you want your conveyor belt to wear evenly, you can put a twist underneath the flat on the bottom surface. So you got the twist going on below, and as the conveyor belt runs through, you always are getting equal wear because now you just have one side. Okay, well, now write down what you think will happen when you cut this one down the middle, okay? What will happen when this is cut down the middle? Anybody predicting anything? No, let's just go right to cutting. Well, you can make your prediction, okay, and write it down and then cut. Oh, we do not have two pieces like before. We have Mickey Mouse. This is such a surprising result. I try these sections out on my husband before I bring them to class, and he thought this was so fun that he tried it out on a friend of his too. Like, sit down, you got to see this. Okay. So we don't get two pieces like we did with the cylinder. Instead, we get one loop. And there's two twists in the loop. Two half twists. And it's long. Well, how many of you need a scissors yet? Do you need a scissor in the back? Do you need a scissor yet? Do you mind? You're sharing my scissors, right? Can you just like get closer to each other so you can hand it back and forth, please? Okay.
Share with this one.
Oh, you're sharing, Sarah? Okay. Perfect. Thank you. Well, how about another prediction? How many sides? One side. How many edges does the Mobius band have? So we saw that the Mobius band has one side. Write down your prediction of how many edges it has, and then we will get to counting that. Well, that means we need another Mobius band, right? So let's make another one, because we cut the one we had in part. So we get the paper with the tape on it ready to go. We line it up, but then instead of just connecting it, we put a half twist in. So we have our Mobius band. It has one half twist. Well, we're going to count the edges by running a marker along the edge, just like we counted the sides by running a marker down the middle. So let's count the edges by running a marker around the edge. And if you have a real inky marker, you can have the ink soak through, which is what I'd like to happen. It has 3 edges. No, I'm just kidding. Not 3. See, isn't this fun? Today's Friday, date night, right? Think what you could do for fun on a date with a Mobius band, right? We could like experiment. Oh, you guys are a hard group. That was a joke, okay? Okay. Okay. So we come back to where we started from, and we see that we have traced the entire edge of the Mobius band without removing our marker and having to switch it across from here to here. We just stuck on the right-hand side, and eventually that covered the entire edge of the Mobius band, because the Mobius band has how many edges? One edge. So the Mobius band is interesting. It has one edge and one side instead of a plain loop. Just adding that half twist in it gives an extra interest to the shape. Remove the edge and remove the side. Now, another prediction time. What will happen if you cut off just the edge? What will happen if you cut off just the edge? So you can write down your prediction. And then we'll go ahead and see. Now, before you cut off the edge, make sure your seam is nicely taped so that when you cut off the edge doesn't fall apart. It's okay. So we're going to be close to the edge here, just a little bit in. And so the other thing to be careful is that you don't accidentally cut through the edge. And all of a sudden, your edge is cut away. So just stay close to the edge there and cut the edge off carefully without cutting through the edge. See, we have one edge, and we're cutting it off. Okay. So what is the result? Yeah, you have two loops. Two loops hooked together. Two loops hooked together. So you have two chain loops hooked together. You have a one that's long, right? One that's long. The long one has some half twists in it, two half twists. How would you describe the short loop? It's that, and we've seen a loop like that already. What is that loop called? The short wide loop is a Mobius band. Yeah. So one is a long skinny loop with two half twists, and the other end is a Mobius band. So we're making models and we're experimenting, and we can continue with that. We can make two half twists or three half twists. So I think we will do that, but I think we'll do half the room with two half twists and half the room with three half twists, and that'll make things go along a little faster, okay? So let's continue on. So we're going to have either two half twists or three half twists. And then we'll count the edges, count the sides, and cut down the middle and see what happens. Okay, so we do that with each of them. Count the edges, count the sides, and cut down the middle. So how about this side of the room does two half twists, and that side of the room does three half twists, okay? So I'm going to do three half twists because that sounds harder to me. So get your tape ready before you do it. And you can confer with the person next to you after you're done to see what the results are. Okay, so you have your band ready to go with the tape. One half twist would be a Mobius band. Two half twists would be this side of the room that I'm on. Three half twists would be the other side of the room. So you can look at the person next to you as you get it taped and see if it resembles theirs. Okay, so count the sides and count the edges. Use your marker like we did with the Mobius band. If you get done before everyone else, then you can certainly try the other one that you did not yet do. So when topologists actually envision these models, they don't envision them as made out of paper. They envision them as made out of a stretchable rubber that they can stretch in any direction they want. As long as they don't tear it or cut holes in it. So topology is actually a very interesting subject. You take things that are made out of, well, you picture them made out of rubber and get down to their basic characteristics. So count the sides, count the sides with a line down the middle, count the edges with a marker down the edge. Until you get back to your original starting point. When you reach your original starting point, then you know you've gone all the way through. So you can cut down the middle once you've counted your sides and edges and see what the result is. Well, I see some of you are still working, but many of you are done. So can you please tell me, when you had two half twists, how many edges were there? Two edges. When you had two half twists, how many sides were there? Two sides. And when you cut down the middle, what was the result?
There's
two loops together. Okay, great. Two loops chained together. What about with the three half twists? How many sides were there? Other half of the room? How many sides? Oh, you did the three?
Yeah.
How many did you get?
Yeah, one.
One side? How many edges?
I think I did one.
One? Yep. And when you cut down the middle, what did you get?
They're chained together with a twist.
So it's one piece though, right?
Yep,
One piece. I did that one too.
connected.
One piece all twisted up.
I don't know. Oh, that's cool. Oh, that's so cool.
Does anybody want to make a conjecture now? Because we looked at no twist, one half twist, two half twists, and three half twists. Does anybody want to make a generalization?
even twists, they'll have 2 edges and 2 sides, and if they're odd, they'll have one.
Good. If they're even twists, they'll have 2 edges and 2 sides. If they're odd twists, they'll have 1 edge and 1 side. Half twists. So what we use most is the Mobius band out of all of these. So that's what we're going to spend more time investigating. Why do you get just 1 edge and 1 side when you add that half twist? And to do that, we use what's called an identification diagram. So an identification diagram is a pattern to give directions to how to assemble one of these 3-dimensional shapes. So it's an effort to take a 2-dimensional piece of paper and describe how everything's going to fit together in 3 dimensions. So for example, with the plane loop that we made, the plane loop was the cylinder that you just took a rectangular piece of paper and attached the 2 ends together. We indicate that by drawing the rectangular piece of paper and putting an up arrow on the 2 opposite sides. And that just shows that you take the 2 up arrows and connect them and keep the arrows pointing the same direction. So the arrows have to be both pointed in the same direction once you've assembled your shape. So this way we don't get any twisting going on. We get just a direct connection here and make a cylinder. You could also have these arrows both pointing down. It's just so they both point the same way, either both up or both down, to show that when they're looped together finally, like we did here, they're both pointing the same way. So that's my piece of tape with them both pointing the same way. Okay. So then the Mobius strip has an identification diagram, the Mobius band. That has 1 arrow up and 1 arrow down to show that when you connect, the 2 arrows have to be facing the same. So I draw the identification diagram with 1 arrow up and 1 arrow down, and then when I actually make the connection, I'll just do that real quick. So 1 up and 1 down, and then when I actually connect these, they have to be the same way. When you're doing these, you need to trace through the paper so you can see on both sides. So I trace through the paper and see on both sides. Okay. So now when I add the half twist, you see how the arrows are oriented the correct way then? Okay. So that's what the identification diagram is showing. It's showing when you connect, make the arrows point the same way. Well, this is going to help us to figure out why we got the shapes that we did when we cut. So we'll go ahead and make a cut. Okay, so let's draw scissors here, cutting. And my scissors, and they go cut, 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 cut down the middle. And I'll put some more arrows, so because I kind of, whoops, I drew them the wrong way. Put some more arrows because I covered up the one. Covered up so much I accidentally did it the wrong way. Okay. Oh, the screen froze. Oh, that's good. You didn't see my error. Okay. There we go. Okay, so we have the scissors cutting down the middle. We have the arrows pointing opposite ways so they connect. And we picture ourselves along the surface. Now to do that, we picture ourselves as a little insect, little ladybug. Well, you could just picture the ladybug. You don't have to be the ladybug. I don't know. Be the ladybug. No, it doesn't. That doesn't work. All right. So here's your little ladybug walking along the surface. And the ladybug comes to the edge. But wait, it's not an edge because you taped it. So the ladybug gets to the edge, and by the way, this is really a real thing. This is what they do in topology to orient themselves. They really do put little insects on and picture the insects moving. Okay, so anyway, the ladybug reaches here, and where does the ladybug come out? Where have you taped this part of the band? Right here? Is it there? Where did I put this corner? Because I have a half twist. Where did it end up?
On the
Opposite
side.
corner.
Okay, so it's going to be on the left. Where on the left? Bottom, yeah. So when you make your band, you put that half twist in it. So the top moves to the bottom. And that's what's happening with this little ladybug. This little arrow is now coming down here. So ladybug comes out actually on the back side, but that's okay. And it marches along here. And it comes to this edge, but it's not an edge because you've taped it. So where does the ladybug end up? Back where it started. Yep, and it can keep going and it never falls off. And that's why when you cut, you didn't get 2 loops. You only got 1 loop. The ladybug never falls off. It's always traversing, and it traverses this whole thing. Comes over here, hits this arrow, ends up here, goes over here, hits that arrow, comes up there. Let's see if we can use the identification diagram to see why, when we cut the edge off, we got 2 loops. 1 long skinny loop and 1 short loop. So we have these arrows to show that we make a half flip because 1 arrows are pointing up and 1 set of arrows is pointing down. This time we had two cuts along the edge. So 2 scissor marks here, right along the edge. Another scissor cutting along this edge. And the ladybug's staying on the edge. So here comes the ladybug starting up here, walking along the edge, moving along, gets to this point in the upper right, and where does the ladybug end up after it gets to that point in the upper right? It's the same as what we talked about in the last identification diagram. Down here, right? Bottom left. So it comes out down here, only on the back side, keeps walking along, and comes up here again. So the ladybug goes down here, this has been taped to there, goes along here, this has been taped to there. So the ladybug never makes it to the middle. Instead, there's just this long edge that it stays on that's twice as long as the Mobius band was to begin with. And then in the middle, you have this part that the ladybug never touched at all, and that's the Mobius band on your strip. So you have the Mobius band in the strip that the bug never got on, and you have the strip that's twice as long, that's the edge that got cut off, with a loop here and a loop here, a half twist here and a half twist here when it flipped. So you'll need to know these identification diagrams for the quiz. So we did 2 drawings of the Mobius band. You don't need to draw the ladybug and the scissors. You just need to draw the 2 arrows, one pointing up and one pointing down, to show that there's a half twist. Well, I have another shape for you. See if you can picture what this is. So on this identification diagram, there's 2 sets of arrows. So the arrows that are both 1 arrows go together. And then when you're done with that, the arrows that are the 2 arrows go together in a way that the 2 arrows keep in the same direction. So you can assemble that. So let's go ahead and do that. Okay, so you have one arrow, those are going to go together first. And then you'll have these arrows on the ends. And they have to point the same direction once they're connected. Okay, so we'll go ahead and make the long edges go together first. If you have your own tape, this is ideal. A fatter piece of paper works better here, so if you have like a regular half a sheet, that would be ideal. Okay, so we're gonna put the long ends together, and that's what the identification diagram is showing with the single arrows. And before I put it together, can any of you picture what shape we're going to get? I mean, just from the identification diagram that's giving you the directions of how to assemble this, can you picture what shape you get? Now, again, remember, we're using paper, so it's kind of clumsy. If it was rubber flexible, it would be much easier. Can anybody picture what shape? Yes.
A ring.
Yeah, you'll get a ring. Yeah, a donut. So you get the long edges together, and then you bring around the short edges. And make sure the arrows have the same orientation. I think I should have put them together before putting the tape on. You see the arrows have the same orientation here when you bring them around. And ours is paper, so it kind of crushed itself. But if we had a nice flexible piece of rubber that we were doing this with, then it could be an inner tube for a tire. So the identification diagram that we have here then is for a donut or a tire, an inner tube. The actual math name is torus. But you can call it a donut if you want to, or an inner tube, and I will know what you're talking about. We have one more identification diagram that's the hardest, but we can do it. Actually, we can do the best we can in 3 dimensions. This last one needs 4 dimensions to be assembled in its true form, and we'll be talking about the 4th dimension on next Friday. So this next one, you have the long sides together to make a tube, just like we did for the torus. But the short sides have to be connected in a way that the orientation is opposite. So like the Mobius band, it has to have a twist in it. So let's see what you can do with a piece of paper. See if that's going to work out for you. Again, a kind of fatter piece of paper works better for this. Now, as you are marking the shorter ends, some of these will be hidden, and so trace them on the other side as well. So just trace the markings you made on one side on the other side, so they're still pointing the same way. So you get the long sides together. But when you try to bring the short sides together, you see that the arrows are pointing the opposite ways. If you trace yours through on the other side, you'll see it if you didn't trace it through all the way through, you might not see that. So put plenty of arrows on. So you might think, well, it'll be fine as long as I put a half twist in like I did with the Mobius band. But the problem is when you put the half twist in, you're still keeping the arrows going in the same direction. If you put a half twist, no matter which direction you put your half twist, they're still going the same direction. Now you can assemble this, but you actually have to make a hole in it when you're in 3 dimensions. Like I said, in the 4th dimension, you can assemble it without any holes, and you get a shape called a Klein bottle. Have any of you seen a Klein bottle before? The Klein bottle has no edges at all, and it has one side. So the way that we do this is we're going to have to cut a little hole in our paper and feed the shape through. If we had another 15 minutes, I'd ask you to work on it on your own for a while until you achieve that yourself. But since we're closing in on the end of time, I'll show you. You just put a hole in your paper like that. Okay. And then feed the tube through itself. And when you line up the 2 ends, at the end of the tube there, you'll see your arrows. That was the bottom instead of the top. You'll see your arrows have the same orientation. So that's kind of a tricky one. You might have seen a Klein bottle made out of glass. Here's a picture of a Klein bottle made out of glass in your textbook. So there's 4 identification diagrams here for you to know them. The Klein bottle, the torus. Let's write Klein bottle by this one. The Klein bottle, the torus or donut, the Mobius band, and the plain loop. Okay, so you'll need to know those, and also how many edges and sides a Mobius band has. For your class activity, take a picture of the Mobius band that you cut apart. Either one of them is fine. And when you upload that, that will be your class activity. If you have any questions, see me after class, okay? Have a good weekend.